Welcome to Module 202C on Series RLC circuits. This module is going to put together everything that we learned so far about series circuits and build it together to look at what a circuit looks like with all three different types of components in it. This module has been broken down into three different objectives, and therefore we'll also have three different videos to go along with it. The first video is based on the characteristics of a series RLC circuits, about how they're built and why they're built. The second video is going to be looking at the impedance properties of a series RLC circuit and how the XL and the XC interact in order to change my total Z value. The third video is going to be solving series RLC circuits right from the impedance triangle down through power and even phase angles. And we're going to look at how changing one thing is going to affect something else in another section. So let's start with 202 Part 1. The characteristics of a series RLC circuit. The reason why series RLC circuits exist is sometimes we have to do what's called phase shifting. Phase shifting is a practical application that we use in single-phase AC motors as well as in fluorescent lighting in industrial applications. And both of them are done for either providing extra torque or for safety values. When it comes to lighting, we use series RLC circuits in order to combat something called the stroboscopic effect. You may not realize it, but the lights in your room right now are actually flashing 60 times a second. It's too fast for our eyes to see, so we don't really register the fact that they're turning on and off 60 times per second. However, they are. The problem is that if we had a motor or a piece of machinery that happened to be turning at that exact same frequency, or any multiple of that, so 60 hertz, 120 hertz, 1800 hertz, for example, any multiple of the frequency of your flashing lights, it would appear as if that motor were not turning at all. This is actually the basic principle behind timing lights for vehicles. If you want to find out if your timing is correct, you set your frequency of your strobe light, and then you can tell what the rotational frequency of the vehicle is if those two line up. So it creates a bit of an optical illusion, and magicians have actually been using this principle for years. You really should go to YouTube, check out some of the videos they have on there. They have some really fun videos that really explain what the stroboscopic effect is. However, what we need to understand as electricians is that that stroboscopic effect can make a very dangerous situation. If you're working in a very loud area with lots of big machinery, and you look at a motor that's supposed to be turning, but doesn't look like it's turning, and you reach down to touch that motor, you could lose your finger, or even worse, you could kill yourself because of that. So since that can be a dangerous situation, we want to eliminate the stroboscopic effect in certain applications. The way we do that is by putting a phase shift capacitor in series with one of the lamps in our fluorescent fixtures. Generally, they're built right into the ballast, so you don't even know that they're there. The concept behind this is that if I put a capacitor to shift the phase of one lamp, then they're not flashing at the same time anymore. One is slightly off the other one, so there's going to be no point in time where I don't have solid light. Yet they're both still operating at 60 hertz. One's just slightly ahead of the other. The other example that we would use a series RLC circuit is in a single-phase AC motor. In order for a motor to rotate, we need to have a turning magnetic field. Once we have that turning magnetic field established, then the rotor is going to be pushed along by that magnetic field. In three-phase motors, that's easy because we automatically have that rotation happening within the three phases that are all offset from each other. However, in an AC single-phase motor, we don't have that same effect. So, with our single-phase AC motors, we actually have two different windings in there. We have the running winding, which will create that magnetic effect as we go through its cycle, but we also have a starting winding. And within that starting winding is a capacitor. The job of that capacitor is once again to do a phase shift. So now when I start this motor, I'll have one winding firing 90 degrees opposite the next winding. And that creates this rotating magnetic field that's enough to get that rotor started. Once the rotor is started, that start winding is on a centrifugal switch and it is taken out of operation, since that capacitor was never really built for full-time operation at all. And once it's rotating, there's no real advantage anymore of having the dual magnetic fields. So this is what our diagram for our single phase motor looks like. We have a running winding and our starting winding, and in series with our starting winder is our capacitor and the centrifugal switch. The running winding, once again, creates enough magnetic field to keep the rotor turning, but in order to start it, the start winding creates another magnetic field at 90 degrees, which gives it direction. So that's the end of part 1 for 202C. Return to Blackboard, do the knowledge check, and continue on to 202C part 2.